Everyone for coming to our monthly tech talk. We are really excited today because we have the long-awaited using hurdle models to analyze zero-inflated count data. And this is a great subject because we do a lot of counting. And we use a lot of, and it's good to know how to use count data. So I'm going to give some information about the tech talk and the CTR. Please make sure that you sign in and please RSVP so we can better prepare for the next session. Something important, please text 274 to the CME attendance for CME credit. Use the chat feature in BlueJeans if you have technical questions. Make sure you subscribe to the series to learn about upcoming tech talks. And next tech talk will return after the holiday season with matrix envelope models on February 2nd, 2017. That would be very interesting. In the meantime, we have two final ID series presentations this year. Healthy endothelial function on December 2nd and palliative care on December 16th. You can see the full schedule on the ACCEL website, and as always, all the previous presentations are available on our website, DE-CTR.org. So I'm really delighted to briefly introduce Paul Kolm, who is the Director of Biostatistics at Christiana Care, who has been at Christiana Care for at least 11 years, and has a PhD in biostatistics from North Dakota. I don't remember from where. Anyway, has a long experience in biostatistics. He has written many papers and has been co-investigator on multiple grants. So thank you so much, Paul.
So let me begin by saying that this is really easy stuff, except for one part of it, which is a little less easy to understand. So let me begin by giving you some kind of an outline here where I'm going to go. So I'm going to take just a few minutes, a couple slides to talk about analyzing continuous and dichotomous outcomes, to give you kind of a context in which we then put the analysis of count data. And so when we talk about when we talk about analysis of continuous and dichotomous outcomes, of course, we're talking about analyzing data that's at least supposedly normal or fairly normally distributed, and dichotomous outcome would be, logistic regression. In the analysis of count outcomes, there's actually 6 models that that I'm going to deal with. There's actually more than that to analyze count data, but it was just way too much and too confusing to get into some of the others. So the primary one is a Poisson regression, and then negative binomial regression, and then there's a couple of others. Actually, the point or the main topic here, what's called zero-inflated regression. Zero-inflated, it can be either Poisson or negative binomial, and then the hurdle models, which can either be Poisson or negative binomial. So that's kind of where we're going to go. So, as I'm sure everyone here is familiar with this, I probably didn't even need the slides for this group, but just remind you, when we talk about the general linear model, we're talking about analyzing a continuous variable that's normally distributed. And so the general linear model is, some outcome that's continuous, normally distributed as a function of some combination of variables, and of course the b's there, those are regression coefficients. And just to kind of put this in context of some other terminology that's used, if you have just one covariate, one variable, and it's dichotomous, then that's a t-test. Okay, and if you have more than one x, but they're all categorical, that's analysis of variance. So that's where those fit into. They're special cases of the general linear model. And so the important thing to remember about this is that we're talking about normally distributed data, although what's probably more important than that is the assumption that the residuals, that is the difference between the observed outcome and the predicted outcome from the model, that those residuals are normally distributed with a zero mean. And that's an assumption of the general linear model that's probably the most important one to think about. And so we can plot what's called a normal quantile plot of the residuals against a normal distribution. And so if the plot looks like this, we're in good shape. So we can, the assumption of our model has been met. On the other hand, if it looks something like this, when you plot the residuals against the normal distribution, it looks like this, then we're in not so good shape. In fact, we have to do something else besides the regular regression to handle this. But that's another tech talk in and of itself. I'm not going to go there, how you do that. Okay. So then an extension of the general linear model, the generalized linear model, and the most familiar one, of course, is the binary logistic regression, where we model the log odds of some event. And so this is the log of the probability of the event over the probability of no event. And it's modeled in the same way, where you have some combination of variables that you think are predicting that outcome. And then the sign of the regression coefficients is the same sort of thing as in regular linear regression, the way you interpret them. If statistically speaking the b's are 0, then there's no linear relationship in the log odds x or the predictor variables. And of course, since we're modeling log odds here, then as you all know, if you exponentiate the regression coefficients here, you get an odds ratio. So that's pretty familiar. If you have more than one category in your outcome, though, we can also handle that by ordered logistic regression, or if the outcome is not ordered in some way, it's just categories that are nominal, then we can do multinomial logistic regression. But again, that's another talk.
Back in May.
Okay. And so, when we talk about the normal distribution for the general linear model, then for the generalized linear model for a dichotomous outcome, this is our logistic regression curve, or logistic distribution. And you might say, well, that doesn't look very linear to me, but it actually is right through here. And so when it's not linear, of course, is in the extremes. And so just this is a free piece of information. When you look at an analysis in a paper that has really big or really small odds ratios, you're probably at the extremes here, and so that when the model kind of falls apart, so to speak. Okay, so then another that's somewhat different from the dichotomous outcome, the generalized linear model still, but we're going to analyze counts. And so the distribution to do that is the Poisson distribution, or Poisson count, where we're talking about a count for over some unit of time. And that's an important part of the Poisson distribution, is that we're talking about a count over some particular unit of time. Small counts are typically right skewed, but as the counts get large, then the Poisson distribution tends to look like a normal distribution. So the Poisson distribution is defined by its mean. It just has one parameter that we use to define it, and that's its mean. And the normal distribution is defined by two parameters, its mean and standard deviation. But for the Poisson, it's just defined by the mean. So The mean is interpreted as the rate of occurrence or the expected number of times the event occurs over a given period of time. That's what the mu is here, is the mean, and the y is the count. So the thing about the Poisson distribution is that the mean and the variance are equal if you have a true Poisson distribution. Okay? And in that case, we refer to that as equidispersion. But of course, as typically happens, that may not be the case. And so if the variance is greater than the mean in the distribution, then we call it overdispersed, or that's overdispersion. Of course, the opposite can happen. If the variance is less than the mean, then it's underdispersed. We're going to primarily just deal with overdispersion because most count data in medical research is overdispersed. That's been my experience. I don't think I've ever seen a data set, count data that's been underdispersed. And most textbooks that you read will say that very infrequently do you encounter underdispersed data, but it can be handled. Okay, so here's an example of count data. This is from the Bridges data, and this is what I'm going to focus on is readmissions and showing how we model this. So this is readmission within 30 days of discharge. Okay, so it's obviously an occurrence over a given period of time, in this case 30 days. And so here's the distribution. Obviously most people aren't readmitted, but you have some that are readmitted. But then you also have a few people here who are admitted more than once. So that's our counts. So we have 64 individuals who were readmitted twice within the 30-day period, and 7 individuals who were re-hospitalized or readmitted within, or 3 times within the 30-day period. And so this is what the distribution looks like. Obviously, it's right skewed. On the other hand, if we go to the other extreme, and we look at heart rate, which is a count, because you're counting beats per minute, but that's typically a large number. If it's a small number, then you're talking about a different set of, or a different population than you are with people with a normal heart rate. So what we find then is like heart rate tends to be normally distributed. So when we analyze heart rate, we analyze that as a continuous variable, not as a count. And so you can see I've got the of the population over the sample of heart rates that I had. This is the distribution, and so this is the line is the empirical distribution. And if you overlay it with a normal distribution, you see that it's pretty close to a normal distribution. So if we have a count that's really large, or like heart rate, then we'll analyze that as a continuous variable, as a normally distributed continuous variable. Okay. The other then distribution that we're going to look at is the negative binomial distribution. And what that does is it adds a dispersion parameter to the Poisson distribution. And so it looks like this, where you have the mean, and then you have plus some dispersion parameter times the mean, or sometimes there's different forms of it. But basically, what that does is allow you to handle over dispersion or under dispersion. If the dispersion parameter, which is usually labeled alpha, if that's equal to 0, then you have a Poisson distribution. So that's what the negative. So if you have count data that's over dispersed, the negative binomial distribution is going to fit better than the Poisson distribution. Okay, now we get to the hard part. So one of the things that we need to talk about when we talk about count data is, what about zeros? Because 0 is a count. Okay? So we can have a distribution where we have no zeros. And we refer to that as zero-truncated. And so an example of that would be length of stay, where you have length of stay in the hospital as an integer value, like 1 day, 2 days, 3 days, so on. You can't have a 0-day hospital stay in your data set if you're talking about people who were hospitalized. So we call that zero-truncated. Okay, then we can have a distribution where, given the mean of that distribution, of the Poisson distribution, we have too many zeros. Okay.
That's typically like the 30 days readmission things, right? Where there are too many zeros.
Right. That would be probably the best example. As you remember, in the distribution where we looked at 30 days, we had a lot of zeros. So the question is, do we have, given the mean of that distribution, and assuming it's a Poisson distribution, are there too many zeros? Well, if you can have too many zeros, then you can also have a distribution with too few zeros. Okay. But, and then this is the difficult part here, we can have a distribution with what I've called structural zeros. And what I mean by this, and the proper term for this in the literature is what's called zero-inflated. And what we mean by this is that there might be some individuals in your data set who have a zero count, but they can't possibly have a non-zero count, or a count greater than 0. Now, I borrowed the term structural here from contingency table analysis, where a structural zero means that you have a cell in your contingency table that is empty, but it can't be anything other than empty. There's no possibility of there being an actual count in there. So let me give...
I have a question. Why would it be a problem that there are too few zeros? It seems that it's just ideal situation where you don't have any zeros.
Well, but then it might not be Poisson distributed. Is the problem with that? The same way with the too many zeros. When I sort of first got into this, I thought that's what zero-inflated meant, was a too many zeros, which I still think is kind of a good description of too many zeros and zero-inflated. And too few zeros would be underinflated. But technically, zero-inflated refers to this phenomena where you have zeros that can't be anything other than 0. And so I tried to think of an example of this. And so let's say that we have that the hospital sends out a questionnaire about smoking behavior. And so in the hospital, they want to find out the number of cigarettes that patients smoked during the week. Now, I know they can't smoke in the hospital, but forget some of the realities here. So they sent out this questionnaire, and they didn't consult the value institutes, so they didn't include a question here that asked, "Are you a smoker or not?" So okay, so you can have two kinds of zeros here. You can have what I call a smoker zero. That is a person who is a smoker, but he or she didn't actually smoke during the week. Maybe they're trying to quit. So during that time period when they counted, the number of cigarettes you smoked, they didn't smoke. So that's 1 0. But you can also have what I call the non-smoker zero. So in other words, the person who doesn't smoke at all, or has never smoked, there's no other possibility than 0 for that count. And when you get the questionnaire back, you don't know the difference. You can't, because obviously it's and you didn't ask the question there. So in zero-inflated models, what we're going to do is we're going to model 2 types of zeros. And so the analysis is there's 2 parts to the analysis. We're going to analyze 0 versus non-zero. In other words, that's just going to be a logistic regression, okay? Because that's a dichotomous outcome. And then we're also going to do an analysis of the actual counts, but we're going to include the zeros in that analysis. So this is the Poisson or the negative binomial regression here. And you got to remember this includes the zero count. So we're actually analyzing zeros 2 different times here when we do zero-inflated models. In some disciplines, they refer to these as good and bad zeros. So in this case, the non-smoker would be a bad zero, okay, because it can't be anything other than zero. Whereas a smoker's zero would be a good zero, which seems contradictory, but that's the way we would interpret it in that context. Okay, so any with me so far? Okay, so here is a slide that you'll need to be familiar with for the final exam next week. So when we actually do a zero-inflated regression analysis, we have 2 parts to it. We call it the inflation part, which is looking at just the zero versus non-zero, and then the count part, which includes zero, and then the other non-zero counts. Okay. But when you go to calculate the the predicted count, both of these are taken into account. So this is in words, and this is the actual calculation. Okay. Now, I know that this is probably not going to be something that you really care about, but what I want to point out here is in this calculation, you notice that I have 2 different expressions in here where the x's are the covariates and the b are the regression coefficients. One is subscripted by little b. That refers to the binomial component, binomial calculation, the logistic regression calculation. If it doesn't have the subscript, then that's the count component. And so when you actually get a predicted count, or the mean, whatever, you calculate this by both of these are included in there. So when you get a predicted count or predicted mean, it's taking into account both the logistic regression, or the binomial part, and then also the count part. That's all you need to remember. Okay. So when we do a zero-inflated Poisson regression, that's what both of those. In other words, think of it this way: we're doing 2 different calculations, but we're including zero in both of the calculations. And so we're going to come up with one prediction value for the mean of the distribution. Okay, then now it gets really simple again. Hurdle models. Okay, these are 2-stage models where we seemingly do the same thing as we did in the zero-inflated model. We have a logistic regression part where we calculate the zero versus non-zero and get a predicted probability for that. And then we do the regression of counts, except at this time we're doing a zero-truncated where we're not including the zeros.
Why would we do that? Why would we do that? So
that's where the idea of hurdle that comes from. That the first part of it is you hurdle the zero count, and then if you are past that, then we're just going to model the non-zero part, the non-zero counts. So this is a way of getting past having too many zeros. So we're just in this part of it, we're not including zeros in the analysis. It's just the accounts of the counts of 1, 2, 3, or whatever the counts are. Okay. Like I say, now it gets really easy because this is straightforward. And And in this case, then the models are not combined like we did with the zero-truncated one. So we're actually going to get two different pieces of information in a hurdle model. We're going to get the probability of a non-zero count, and then we're going to get the rate or the mean of the non-zero.
That's very satisfying, actually. It's simple to understand.
Mm-hmm. It is. I say it's straightforward.
But what do you use it for? I guess that's what I don't understand. What example would you use it for?
Bridges.
Well, the readmission one would be a good example of that, because we have a lot of zeros. So you want to get are you going to get readmitted or not? And then if you do get readmitted, how many readmissions do you have?
This is good.
And you can see
because here's the issue that I have, and I bring this up at the end. Typically, the way that readmissions are analyzed is just readmission, yes or no, regardless of how many readmissions a person may have had, which kind of amounts to analyzing first readmission, because you're ignoring any more than one readmission. The problem with that is you're ignoring some readmissions, so you're actually underestimating your readmission rate, because like I say, you're excluding some readmissions. But this then allows you to include the other readmissions that a patient might have that had more than one.
So the other thing about the zeros here, it's like your smoker thing of your the zero readmissions. You have two types, basically. You have lots and lots of people. They were never going to be readmitted. There's almost no chance they're going to be readmitted. And then there are the people who have a real chance of being readmitted. Now, obviously, I'm simplifying that.
Yeah.
But I still think that there's something to that.
Yes, and that's the question. I'm going to bring that up at the end when we talk about readmissions. Is there such a thing as a structural zero readmission? Okay, so like I say, hurdle models are straightforward. They're really simple, and they're simple to interpret. So we're going to develop 6 different models here on readmissions. Just the normal Poisson regression negative binomial. Then we're going to do a zero-inflated Poisson, a zero-inflated negative binomial, and then a hurdle Poisson and a hurdle negative binomial. And then we're going to pick which one of these is the best by using the information criteria. I'm sure everyone remembers my discussion of this from when we analyze this data using time series. So just remember that for the information criteria, smaller is better. So, the smaller the information criteria, regardless of which one we use here, that's the better model. It doesn't mean the model's right, it's just better than the others. Okay, so what I'm going to model is, using the Bridges data, I'm going to model 90-day readmission for specifically inpatient, non-elective readmissions of just PCI patients. So the population of patients here for the Bridges data that we have data from patients from 2010 up through the end of September in 2015. Then I'm picking a set of patients for which we had follow-up through the end of 2015, because obviously I'm looking at 90-day readmissions. I have to have 90 days past their discharge date. So sometime in late September was the last discharge date we had of patients. And so as we did in other analyses, what we're interested in is, did the Bridges program or the CareLink program reduce the admission rate? So as before, I've divided this up, the Bridges component into 3 different categories here: the pre-Bridges, and the Bridges year 1, and Bridges year 2, although year 2 is a little longer than an actual year. But and the reason that we do this is because the Bridges program, the CareLink program, obviously that's not something that's implemented overnight. It's implemented over time, and so you wouldn't expect to see any effect until further down the road. So that's why we have year 1 and 2 bridges. And then what we're doing is we're going to model 90-day readmissions as a function of the bridges component here plus some covariates. And as I mentioned before, the way that this is, we actually did this, or way it's typically done, we're just going to analyze readmissions just as a yes or no. But if we do this, then we're ignoring the other readmissions that some patients had if they had more than one readmission. And then these are the covariates that we're including in our model: age, sex, race, insurance, the Elixhauser comorbidity count, which is entered in as a continuous variable at range from 0 to 30, elective and transfer, which are yes, no's, and previous hospitalizations within 6 months, current hospitalization. I'm also analyzing that as a continuous variable at a range between 0 and 22. And then length of stay, because in this case we calculated the length of stay using the clock, so you can get like 1.5 days, or 1 3/4 days. So that's typically a non-integer value that's greater than 0. And it's continuous. Okay, so getting to the results. So these are the demographics. There were almost 4,000 patients pre-bridges with over 4,600 hospitalizations. So this is the analysis taking into account the fact that some people are hospitalized more than once. And then year 1 and 2, you can see that the age is pretty similar for the three components. The distribution of males is pretty much the same. There's a somewhat fewer whites in year 2, but it's fairly similar. Okay, so
Paul, is this the same population that's followed over time?
No.
No, okay.
Well, some for the readmission,
Some
yes, but
right,
it's a different population. It's a different population. The ones who were, pre-bridges, intermediate and post-bridges. It's totally different patients.
okay, so here is the 90-day readmission counts. We have the observed counts, and then this is the expected counts if we assume it's a Poisson distribution. So we can look at this and we can see right away what the issues here. We have somewhat more zeros than would be expected, although not that many more. We can see that there are fewer than expected people who had one readmission, but we have more than would be expected that had 2 or more readmissions.
So over-dispersed.
So it's over-dispersed. And if we calculate the mean variance, we can see that that's the case. So the mean is 0.16 and the variance is 0.23. So obviously we have over-dispersed data. So right away that's going to tell us that our negative binomial regression is going to probably be the best regression. Okay, so get to the models. So this is the Poisson, assuming we have a Poisson distribution. And so we can see that, I'll just sort of focus on our bridges analysis here. So 3 bridges, obviously that's the reference group. So we can see that there was no difference in the IRR stands for incident rate ratio. It's obvious, analogous to an odds ratio, but it's the rate. So you can see that if we just look at the point estimates, that in year 2 we have about a 13% decrease in incident rate, which we think, oh wow, which that's another argument, but you can see that's not statistically significant. I have a question about, if you do this kind of stuff, do you want to set your significance level at 0.05 or should you maybe put 0.1? That's another. Okay. Then the negative binomial, we get about the same point estimates here, 14%. decrease in the rate over year 2. So here's the zero-inflated Poisson model. So this is the inflation model. So remember, this is 0 versus non-zero. So this is actually an odds ratio. And this is the count model part of it, where we have a rate ratio. So we can see, if we focus here, because this is the, remember that this count model is taking into is including the zeros. So we get about the same estimates here of our rate ratio that we did for the other. But it's still not statistical. And then this is the zero-inflated negative binomial model. And again, it's pretty similar as far as the count model part of it goes.
So when you do this type of analysis, do you present both tables, the inflation model and the count model?
Well, that depends on the audience. For this audience, I thought you could probably handle both. Not sure that I would do that. Some other context.
So which table then would you present?
Well, I'd have to kind of think about that. I mean, I'll present a table. Or at least this kind of a table. About that. Okay. So here is our Poisson hurdle model. So now remember, we have, this is a two-part model. So here we're modeling the 0 versus the non-zero, which is an odds ratio. And here we're doing a zero-truncated model, which does not include 0 anymore. This is just the actual counts, or the non-zero counts. So again, this is fairly similar to what we've seen before, and again, it's not statistically significant. And this is the negative binomial hurdle model. The thing, though, that we can do with the hurdle model is we can kind of look at both of these, and we can, include some things that we couldn't with the zero-inflated model. So, for example, you see that when we are modeling just the 0 versus the non-zero, greater than 0, there's a number of statistically significant covariates in here. So, for example, age, previous hospitalization, the comorbidity count, and so on. But if you go to the zero-truncated model, in other words, we're just modeling the non-zero counts, some of these are no longer statistically significant. So what that means is that these variables are impacting whether or not you actually have a readmission, but they don't impact how many readmissions you have. So there's some extra information in doing the hurdle model you wouldn't get from doing the other models.
So this is also very satisfying to look at. I'm not surprised that age predicts whether you come back or you don't come back. But comorbidity, look at that. All of a sudden it's
comorbidities impact both. Whether you actually get readmitted and then how many.
So if you have six comorbid states, you're going to have a high IRR.
Okay. So now what we need to do is then we need to choose one of these models.
Let's transfer. I just want to. What does transfer mean?
Transfer from one hospital
From one other. So those, whatever analysis, whatever kind of analysis we did, those both, whether it was an elective and transferred, ended up being statistically significant, and they were either odds ratios or rate ratios less than 1. Okay, so our information criteria, and so to begin with, there's a couple things I need to point out here. When we do the hurdle models, you get the information criteria for both components. So to look at obviously the overall one, you need to add those together. So that's why I've highlighted these here for the total. So that's the information criteria you need to look at when you compare it to the others. Okay. So then I've highlighted the ones, remember, smaller is better. So if we use a Kaiki's information criteria, then the zero-inflated negative binomial one is the best one.
Well, not by much.
But not by much now, because it's fairly.
It's amazing. It's actually amazingly constant.
I'm sorry.
It's amazingly constant. Very similar across.
Yeah. We get a different conclusion though if we use the Bayesian information criteria, which is somewhat problematic because you would hope that those would agree. But the point is that the best models are always the negative binomial model, regardless of which one you choose, because remember our data, our distribution was overinflated. So
You mean overinflated or overdispersed?
I'm sorry, overdispersed.
So the zero-inflated is the one where you do both and you count the zeros in the second one.
The zero-inflated one, right, is where we do model with just the zeros versus non-zeros, which is a logistic regression. Then we do the count model, the Poisson or negative binomial, where we include the zeros in that. And then, as we'll see in my next slide, when we get the predicted values, those are combined.
So are you surprised at how similar these are across different models?
Well, yeah. I mean, they clearly the negative binomial models are always better, what I expect. The fact that there is a difference here, there's like a 20-point difference, and again, that's pretty arbitrary, but most people say that if you have something greater than a 10-point difference, then take that one, you know. So, but I don't know that there's any, you know, it's kind of like the I-squared analysis, what you call small and what's large. But if we just go strictly by, you know, which one is the smallest, then this one is. But pretty close. Okay. So here are the unadjusted rates, which of course are the same, obviously, which, you know, regardless of which model here. That's why the rates are the same over the year 1 and year 2, and then these are the adjusted rates from the model. And I did just the negative binomial ones because obviously those were the best fitting. And so we get about an 10 to 11 percent rate using just the negative binomial. If you use the zero-inflated, then the adjusted one is about 13 to 14%. With a Hurdle model, as I mentioned, we get two pieces of information. So this is the rate for just having, or just for having, for being readmitted. Because remember that this part is just the zero versus the non-zero. But then we have the second part of the model, where we analyze just the non-zero counts. So this is the average for the 3 years over the actual count. And so again, you can see for these that like when we looked at the actual models, do not statistically significantly different. But we didn't probably expect it anyway, because there's going to be it's really hard to show that an intervention does something.
We've noticed.
Period.
So you interpret that as that's 12 per 100 people who've been readmitted, yes, no? the 12.3.
Right, but they would be, yeah.
And then it's an additional 1.23 per 100.
Right, then for those who were readmitted,
yep.
then the average readmission rate is 1.2.
Okay, thanks.
So why don't you do the same thing for the zero-inflated? I mean, shouldn't you have also two rates, because you have the logistic regression first and then the...
But that's not the way that it's computed, because remember in the formulas that when you calculated the rates, they included both the zero versus non-zero and the count, but the count also included the zeros.
That was your formula with the beta
with
script,
where
they had both
b
in there.
Okay.
Yeah.
Oh yeah, the little b.
The little b, then that had one number.
Yeah.
Versus the two series.
Right, the slide you need to remember for the final. Okay, so on here. So conclusions. So obviously the 90-day readmission data was over-dispersed. That was pretty clear. We had slightly more zeros than Poisson predicted. The negative binomial models, regardless of which one we used, are the best fit because we had over-dispersion. So the zero-inflated model might be appropriate. And the reason that I thought that it might be appropriate is because of the possibility of a patient dying within the 90-day period. So once they die, then their possibility of readmission is zero.
That's a good point. That's a perfect example.
Now you would think that we had hoped that we'd have that piece of information. We did not in the bridges. For whatever reason, we couldn't seem to figure out if people had died or not. We weren't able to get that information. But because it's a possibility, then we still have that. So some of the zeros might be zero-inflated. That is, there's no possibility of being an actual non-zero count. So the fact that the zero-inflated model was the best model, makes some sense. Okay, as I already mentioned, regardless of the model, the negative binomial ones fit best. We have somewhat different on the information criteria, but and then the conclusion that obviously that you'd be interested in if you were writing a paper, make a presentation, there's no significant change over the bridges years. So, and then as we saw when we looked at the hurdle model, that previous hospitalization, length of stay, elective transfer, they influence the probability of being readmitted, but not how many readmissions patients had. On the other hand, comorbidity influenced both of those. So that's kind of an interesting sort of conclusion that you can make by doing the hurdle model. Okay, so to summarize, when the distribution is over-dispersed or under-dispersed, you want to always use the negative binomial model. Zero-inflated models are only appropriate when the zeros is the only possibility for some patients. In other words, if you have data where zeros mean that they actually didn't have a count, but they could have a count, then the zero-inflated model is inappropriate. So even though it might show up as, you can still do the calculations and it might show up as better, but from a theoretical standpoint, it's not appropriate. And then finally, that the hurdle models provide two pieces of information. We get a zero versus a non-zero probability, and then we get a mean of the non-zero count. So these are some references that you might be interested in. The one by Hill or Hilby, however you pronounce that, is really pretty good. This is very very readable book. He has a book that's unreadable, but on count data, but And then there's two Stata Press books that include analyses for count data that you might find interesting or helpful. And I will mention that Stata has built-in routines for doing count data, including the Poisson. Some of the ones of using like the hurdle models, Bill has written routines in Stata and also in R that do the models that I've done. And some it kind of you can get to the same conclusions, but just some of the routines that are regular Stata routines and some that he's written are just they're easier. They give all the information in one run rather than having to do, like in the hurdle model, you can get that by doing a logistic and then by doing the count data, but then you have to do some addition to get the information criteria and so on. So that is count data. Thank you for your time.
So I have a quick question. So when you do the zero-inflated, do you have to identify the people, the records that are not going to have any records that have the structural zeros in advance?
No. Because, and you may not know that, like in the rigid, we didn't know that because we didn't have death data. Well, we did, but it turned out, I guess it was unreliable or something. I can't remember why, but we couldn't use that. Right. So if you knew that, then your analysis might be a better analysis might be survival analysis because you would have the time. You would know the time when they died and the time when they were readmitted. Do the analysis as a time to event survival analysis.
It would be better. I'm thinking about Engage actually, where I think we used a Poisson, a zero-inflated Poisson. I have to ask Bailey, but I think that's what we used. But we decided to exclude the patients who died. So maybe that was not the right thing. We should have included them and do and keep the zero-inflated. It's related to readmissions also.
Okay. Yeah, it sounds like you're throwing away data. I have to look at it, but yeah, that would be. Yeah.
So it's kind of strange, actually. I mean, that you don't have to identify the people or the records that have structural zeros. You just assume that you have in your population structural zeros. That's what you do.
So one example of the difference between good and bad zeros, that terminology actually comes from, I guess, ecology. So like in counting animal traffic through some particular point or region or whatever. So if they set up their counting mechanism, whether it's some person just being there and counting or camera or something like that. So in just the under normal conditions, then you would get a count of, say, how many animals or how many birds you saw. But if, say, some campers came through and they scared everything away and you had a zero count, then that's a bad zero because that's a zero that's structurally it's a structural zero. In other words, it couldn't be anything other than zero because nobody, no animal is going to come, through, at least for a while. Anyway, that's if you have count data to analyze, it's sort of actually fascinating.
So do you try to use something else to determine what are the good zeros and what are the bad zeros? Like, so say that they only asked a question about smokers, but then maybe there was something else that alluded to smoking, and then you use that to try to break out the bad zeros and the good zeros, or you're just making that assumption, period?
You'd have to, an example I gave, which was maybe not a good example, you'd have to you'd have to assume that there were some in there that if they
Okay.
just generally surveyed people but didn't ask whether they were a smoker or not.
Okay, so you
Some
don't
of
have to
the-
make that determination yourself.
No.
You're just assuming.
Right.
Okay.
That there would be non-smokers in there and that they would be zero, that there'd be no possibility of their having a non-zero count. And then that was the same thing with our readmission data here. Within the 90 days, there could very well have been some people who died a week after they left the hospital or something, so they would have a zero count. But you don't know that.
Have you seen comparisons, like Claudine was saying, between models that would just remove those people who died because they have no likelihood of event if you know, or give them a zero and use a zero-inflated model? Or use a survival approach? Well, I guess. Yeah.
Well, it's the thing like I mentioned with if you just analyze, say, readmissions as yes or no, regardless of how many some people may have had, and you're ignoring some you're basically throwing out some data
Right.
that may affect your model.
Interesting.
Terrific.